And so, welcome everyone to the University of Hawaii Institute for Astronomy, Haleakala Division. I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist. And I've put together these talks. And this month, Mark and I have had a number of discussions about climate change and the politics surrounding that. And so I twisted his arm, and he volunteered, and so he'll be giving the talk tonight. Dr. Mark Willman, his first comment about how I should introduce him is that he likes living on a habitable planet. Okay? So he received his PhD at the University of Hawaii at Manoa, and he was studying asteroids, focusing on space weathering. He went over to the 88-inch telescope after that, and then he was hired by the Penn Stars Observatory, who many of you have heard. They found somebody's trying to start an interstellar snowball fight with us. And they also had part in the optical detection of the recent LIGO observations. So they quite an impressive observatory, and Dr. Willman is a very nice asset for that program, and we're really glad to have him here. And let's give him a nice Maui welcome here.
Thank you, JD, and welcome everybody to the fourth Friday talk here. This is the third and final talk in a series of three talks that have followed this common topic, which is related to habitable planets. And the first one was in April, and that time I discussed an amazing discovery of TRAPPIST-1. It's a small red dwarf star about 40 light years away. And it has 7 planets. Oops, it has 7 planets strung out like pearls on a necklace. And the startling thing about these is that they're all Earth-sized. Nobody ever expected this kind of thing. It's very unlike our own solar system, where we have the inner terrestrials and then the gas giants and ice giants outside. 7 Earths in a row, almost identical to Earth's size. And so we looked at the other conditions necessary for habitability, the temperature and so on. And it turns out that there's a chance, we don't know, but at least 3 of them, 3 of the 7, are in the habitable zone. And the other 4 may also be habitable due to tidal locking, which is peculiar circumstances. Anyway, if you want to go into the details of that talk, it's on our archive on the IFA website. But then in July we had our open house, and so I did a little short talk about extending this topic of habitability from deep space, 40 light years away, back to our own planet. And in particular discussing climate change, so the rising temperatures on our planet. Now this is a kind of a hot potato politically right now, as you may have seen in the news. Is this true? Is it not true? Is it serious? Is it something we don't need to worry about? So as I'm standing here in my role as a scientist tonight, I'm going to do my utmost to be objective and impartial and just present you with the evidence, and I will let you draw your own conclusions about what's going to happen in the future. If you push me on my opinion, I may reply, but I'm going to try and stay out of the dogfight here. And so the climate of science, now that clever wordplay is due to JD's suggestion, and this is a science talk on climate, but we're going to slightly drift into politics here because this is a little different than your typical science discussion, astronomy discussion, which is usually pretty abstract. We're talking about things that are far, far away, long, long ago. This particular topic happens to impact us directly and maybe in the near future. So let's see what we've got here. Okay, just a quick review. These are the 7 planets around TRAPPIST-1, 40 light years away. And for comparison, these are the correct sizes and, of course, the correct shape. But the colors, ignore the colors. That's the marketing part. We really have no idea what the colors are like. But for comparison, here's our own terrestrial planets, and this is our favorite one. And so look at the size of this compared to these. You see they're almost identical. There's two of them here. Now these statistics about the orbital period, the distance from the star, the radius of the planet, and the mass of the planet, these are highly accurate because they can tell the radius accurately by how big of a shadow the planets cast when they cross the star. And they can tell the mass by how each planet perturbs the next one when it goes by. They get jostled slightly. So these are actually quite accurate numbers. And you'll notice the two smallest here, these are cleverly named B, C, D, E, F, G, and H. And you see D here is 0.77. It's 3/4 the radius of Earth. And so is H. Those are the smallest. The biggest one is 1.1. It's just slightly larger than Earth. But 7 in a row, almost identical to Earth. And the amazing possibility is that all 7 could have liquid water. That's our criterion for what defines habitability. Can you have water oceans like Earth does? Now, we don't know that's absolutely essential for life. We think it is. Every species on our planet requires water. So we may be extending ourselves unduly, but as far as we know, water is all through the universe. It seems like it's a critical ingredient for life. So, but to get to the details of that, you can look up that talk and read more about it. But these were the 6 factors we considered: the temperature, water, gravity, atmosphere, radiation shielding, and life. And as I said, the temperature we think is ideal. 3 of them are actually in the habitable zone that you can calculate just mathematically where the temperature would be right because of the distance from the star. And the others may be tidally locked, which would allow a habitable zone on the planet. Maybe the tidally locked means you always keep the same face to the star when you go around it, like our moon does to us. So, of course, if you're going around a star and you're always pointing in the same direction, stand in the light. Then the close side will get very hot, and the far side will be very cold, frozen over. In fact, that's how you know those colors that we saw in the previous slide are not right, because some of them are tidally locked. Certainly, there would have to be a discrepancy on the 2 poles. The far pole would be ice, and the near pole would be very dry, presumably. But because of that, in between ice and dry, there's probably a Goldilocks zone. So you can think of that, a ring around a planet that could have a water ocean. That would be very different than our planet, wouldn't it? The gravity, because we know the mass and the radius of the planet, we can calculate the gravity. It turns out they're all fairly close to Earth. There's 1 or 2 maybe that would be difficult to move around. You couldn't walk very far. You would weigh so much there. But it's not, let's see, what was it? It was like 50% more or so. They're all reasonable. Some of them are lower gravity, but none of them are very light, none of them are very heavy. They're all approximate. Now, the atmosphere, that's the big unknown. And radiation shielding, that would work because you can always hide on the backside of the planet, even if the M dwarfs are known for putting out flares, particularly when they're young. And so that would be dangerous if you're facing it, but you can always hide in the back. So the moral of that first discussion was that while TRAPPIST may be a nice place to live, we're not sure because we don't know about the atmosphere there. That's the key unknown variable. And bottom line, you can't get there from here. It's 40 light years away. People talk about spaceships that can go half the speed of light or something. Even if you had such a propulsion system, which we don't have the foggiest notion of what that would be, but even if you did, you can't go that fast through space because if you do the physics, you realize a grain of sand that you're running along through space in your spaceship at half the speed of light, you hit a grain of sand out there, it's got the energy of a nuclear bomb. So you can't go that fast. You can't even go 10% of the speed of light. You could go maybe a few percent of the speed of light. You saw that movie, Interstellar, where they're asleep for 100 years or something, And meanwhile, there's an accident. A rock hits the fusion reactor, and there's big trouble. So, leads to romance, of course. But so it's not realistic to talk about going a sizable fraction of the speed of light. Let's stretch the envelope. Let's say you could go 10% of the speed of light, which you can't. But the nearest this 40 light year distant star, where these nice planets are, would then require 400 years to get there. Nobody's going to get on a spaceship that's not going to arrive for 400 years. No human being. Maybe when we have robots or something, we'll see. But so the moral of all that was we should take better care of the planet we share. Okay, now let's get into let's come home. This is our own planet, and let's talk about temperatures. What's happening in the temperature? So let me show you the long-term temperature, and then the more recent temperatures, and then the very recent temperature. So here's the long-term. This is 500,000 years. 500,000 years back. So we've got 400, this is years ago, 50,000, 100,000, back to 400 and some thousand years ago. And up the side here we have the temperature. Now there's 3 separate graphs here. These are 2 temperature charts. This is an ice level. The temperature charts, you see, they go up to, this is an arbitrary setting, but the variation here is from about +2 degrees down to about -6 or 7. And these are 2 different locations. This is Vostok and Epica, two widely spread locations on the planet. So that, and you see how well they match. So that gives us confidence that this data is showing something global, not just local conditions. And you see here that over the last 400,000 years, there's been a repeated pattern. You rise up to a high temperature, you drop down, you stay cold. You spike high, you go down cold. Spike, cold, spike, cold. These are ice ages down here. These are interglacials, they call them, when the ice recedes. And here you see the ice is low and high. This is flipped. So when you have high temperature, you get low ice. The ice recedes to the poles. Then an ice age comes back, ice freezes up, covers a lot of the planet. There have been phases in the long ago, this is the last 500,000 years, but in previous parts of the Earth's history, there's been times when there was snowball Earth. The entire Earth was covered in ice. So there has been a lot of temperature variations over Earth's history. But recently, it's in a very steady, predictable pattern. An ice age goes through a 100,000 year period. And then there's an interglacial, and that lasts maybe 5,000, 10,000 years. We are currently right here. So we finished the last ice age about 11,000 years ago. And then the temperature rose up about 8 degrees, and we're now in an interglacial. We've been in this interglacial over 10,000 years now. That's a typical length of an interglacial. So you would expect, if we weren't, am I making a value judgment here? Let's see. If the pattern was continuing as usual, which we'll look at that in a second, then you might expect that this interglacial would soon end and we would start another ice age, which would last for 100,000 years. Now that means game over for civilization, because we depend on this temperature to grow crops, to grow our grain, our Midwest grain belt around the world, in Russia, wherever there's big areas where we can grow grain. That depends on the being ice-free conditions. So this is what made human civilization possible. This temperature rise rose up, the ice receded to the poles, and people started growing crops. And they've been doing that for 10,000 years now. And recently, we've got technology, and that has consequences. Now, okay, so there's the ice age cycle, very predictable over a long span. Now let's look a little shorter time period. This is the last 2,000 years. Same thing again, temperature on the left, and you can see if we start off here 2,000 years ago around the Roman Empire here, we're at -0.4 degrees Celsius. This is Celsius, centigrade. And then there was a little rise over about 1,000 years. It slowly rose about 2/10 of a degree up to about here. These are multiple methods for determining the temperature. Now, these are proxy methods. They're not direct measurements. So they use things like tree rings. You know, when it's warmer, trees grow faster. They get fatter ring that year. So you can cut a tree, look at the rings, you can trace that back, and then you can correlate this tree with that tree over there, and so on. It's complicated. There's also ice cores. They go down to Antarctica or Greenland or somewhere. They drill into the ice. You can determine you can find little bubbles of air that have been preserved for millions of years. And the CO2, the carbon dioxide content, will be correlated with the temperature. You can dig up sediments on the seafloor, take cores, see those layers. You can see when certain animals grew, and you know those animals are correlated with certain temperatures, so you can kind of figure out the temperature that way. So you can piece it together. There's a tremendous amount of work involved in producing this data. But you see what happened was it went up over 1,000 years, then it dropped off a little bit. This is called the medieval warm period. It was a little warmer than usual, about 2/10 of a degree. Then it cooled down over the next 1,000 years until around 1900 here. It starts spiking up in the last century. Now you see it's hotter than it's ever been in the last 2,000 years. And it's moving up fast. This was 2004, and we're now up to, so there's 0.4, 0.6, 0.8, 0.1. We're now up here as of 2017. I'm not going to make a comment. Now, here's the very recent temperatures. Now, these are instrumental readings. This is 1880, goes back to 1880. This is the British Navy. The British Empire was worldwide, sun never set at that time. Here's the, well, the American Empire, I suppose, starts here when it started taking overseas possessions. And this 1907, this is the Great White Fleet. Roosevelt sent around the world to announce the U.S.'s arrival as a world power, and so on. So you see, now these are actual. The British Navy would drop a bucket on a rope into the ocean, pull up a bucket of water, stick a thermometer. It's an actual measurement. But that's only 140 years. We have that kind of measurement. Before that, it's proxies and so on. So these numbers are very accurate. And you see what's going on here. We're around 0 here. These are 1/10 of a degree Celsius again. So we're bouncing around, going along, no big deal. Well, it starts to rise here, like in the 40s. You see it starts to climb a little. When it backs off a little, nothing happens. Boom, 1970. That's the best fit straight line there. We're going straight up. And here we are, 2020. Here's 2010. So this is 2013. Was right along in this trend. 2014 jumps up. 2015. Now look at this rise here. This is 2/10 of a degree. That's 1/10 and a half. That's 0.15 degrees in 1 year. Now remember the 2,000 year thing we saw? For 2,000 years it didn't change more than 2/10 of a degree. It changed almost that much in 2014. Then in 2015, or no, that's 2015, from 2014, 15. 2016 shot up. Now this is the El Nino. This is a weather pattern in the Pacific when the ocean dumps heat into the atmosphere. And it comes around every 5 or 6 years, something like that. So for a year or two, the El Nino was adding to whatever is going on here. We'll think about that. But whatever it was, El Nino boosted that way up. So now we are halfway through 2017. We're almost at the end of 2017 now. The question is, what's going to happen this year? The El Nino stopped last year, so we're now back to normal conditions. So you'd think, well, if this huge spike here, huge value judgment, if this rapid increase is atypical, is just due to El Nino, then this year, it should, or then this year or next year, it should drop back down, you would think, and maybe get it back on this line. But it hasn't. It's the first 6 months of this year are the second hottest first 6 months ever recorded. So, with the only exception being last year. So, we won't have, it'll be 3 months or so before we get the 2017 data compiled. It looks like it may be slightly dropping back from here, but this will be a very interesting data point to see. And then next year's data point will be very informative. So right now, in the next year, 2 years, we're going to see, is this straight line continuing, or has something different started to happen now? Are we starting to shoot up uncontrollably? That's the question. Okay, yeah.
1999 to 2000 on the last graph, you had that much temperature change in the opposite direction.
This one, yeah. 1999 to 2000. Okay, we did have we had here, this is, oh, yes. The question is, you'll see this spike here. This spike from 99 to 2000 actually looks like maybe 98 to 99. But there was a big jump there, and it doesn't seem to have, just seems like it was noise, you know, just a very natural variation. It seems like it went back to this straight trend again. Is this the same thing? Well, that jumped up about 1/10.5 degree. Here we've jumped up 0.3 of a degree. So this is about twice the rise of that. That's why this is exceptional, what's happened in the last 3 years. We've never seen this before. Now this is where it starts getting controversial. The question is, what's the cause? Let me hold off answering that, okay, just a little bit. And let's just talk about some more data. I'm going to start just presenting data. This is going to be a short talk. I only have 16 slides. So I'm leaving a lot of room. Stop me anytime for questions. Do the people online know how to get questions in? Or does that come at the end?
Yeah, they should be all able to.
Okay. Okay, so let me just hold off on that question just for a couple minutes. Here's sea level. Now this is, again, 2,500 years. Here's the temperature. And same kind of thing. We bounce around. Now this is in feet. So 0.2 to 0.4, that would be 0.2, that'd be about 2 inches. So you can see we're bobbling around here, up and down, until here, and around, this is 15, this is 18, 1900, 1920 or something, we start this on sea level. We have now increased 7 or 8 inches. The sea is now 7 or 8 inches higher than it was 50 years ago. And it's shooting upwards. We'll see some, here's projections. Okay, this is 2,500 years. Here's again the recent past, 1800 till now. Till now is here, here's now. You can see there was a slight trend, well, hardly any trend at all. What's that? That's a few inches over 2 centuries it changed. And then it started this spike. Now these are projections. Now most of the data I'm showing you here tonight is from this report on August 7th that was leaked to the New York Times. There's by law, the government agencies, all the government agencies, scientific agencies involved in, associated with climate somehow, are supposed to assemble this report every 4 years and issue it. And as you know, there's a lot of dissension now, even within the government, about even talking about this topic. You might say I'm sticking my neck out. But so the final draft was approved. Or it wasn't approved. It's supposed to be approved by the administration. But the scientists involved were nervous that the administration would try to suppress the report, so they leaked it to the New York Times. So that was published on the August 7th. You can read that report. It's long. It's 600 pages. I'm just hitting a few details out of it. But most of this data is from that report. I've also included a few things from other sources. NASA. So these are projections. Now, this would be best case scenario, least harmful outcome, worst case scenario. And these are based on, I'll show you the temperatures these are based on in a minute, but you can see even if we take the midpoint between outcome 3 and 4 here, somewhere in here, we're looking at 4 feet of sea rise. Now, you know, coastal cities, Houston, Miami, Charlottesville, Kahului. Oh, my final slide is going to deal with Maui. Wait till you see this. It's not going to be pretty. I'll give you a hint. That's going to be a problem if these predictions are right. Sea ice. Look at the ice. Here's 1984. This is the Arctic. Here's 2016. It has shrunk by 40%. Not only has it shrunk in area, but it's shrunk in thickness, way down. So if we project that forward, from 1980, we had 3 million square miles of ice. And September every year, typically. That's the minimum every year. That's when you finish the summer. The main heat of the year is over in the northern hemisphere where the Arctic is. And so the sea ice reaches its minimum in September. And then in October, it starts getting colder. The ice starts to build up again. So it bobbles around here. But you can see the long-term trend. This is the best fit straight line. And now, in 2016, we are down to 1.8 from 3 million square miles. We're now down to 1.8. There's the 40% gone. If you project this line forward, it hits 0 about 2050. But because this is only talking about the area, and we're also interested in the thickness of the ice, the total volume of the ice is what we want to know about. It happens sooner than that. So the projections are that by 2040, the Arctic is ice-free in September. That has implications for the weather patterns in the Atlantic, for instance, because that cold air up there, that cold mass of air, it stabilizes the flow of air around the Atlantic up through Europe and so on. Once that's gone, weird things are expected to start happening. Cold surges will surge down the east coast of the U.S. and so on. Also, the reflectivity of ice is almost 100%. Reflecting sunlight hits ice, it almost all bounces off. But once you melt that ice, you have open ocean water. It's much darker. Now you absorb the heat. That's a positive feedback loop. So the warmer it gets, the warmer it gets. Okay, solar irradiance. Now, is Jeff Kuhn in the audience? He's stepped out. Okay, this is lucky. Jeff Kuhn's old friend of mine. He's a very good solar scientist. If he was here, he would quibble over this data. He said, blah, blah, blah. He'd say, no, Mark. Now, I'm taking this out of the report. I didn't generate this data. But a caveat here is that there are solar scientists that would quibble over this. The main point here is from 1950 to now, 2020, you see this pattern, this cycle. Up, down, up, down, up, down. There's 1, 2, 3, 4, 5, 6 cycles here in 70 years. That's the solar cycle, 11-year solar cycle, right? The sun has sunspots, heavy sunspots, and then they go away, and then 11 years later they come back. That's been going on since Galileo. Well, it's been going on since presumably the beginning of the sun. But we've known about it since Galileo, yes. So, okay, fine. let's look at the amount of change here. These are watts per square meter. So how much energy lands on a square meter of Earth? And it's about 1,360. The highest point here is 1,362 something. And the low point is about 1360.6. So that's a difference. The whole range of variation here is 1 watt would be 61.6, about 1.5 watts out of 1,300 watts. So that's 1 part per thousand. So the sun doesn't change temperature much. It's a part per thousand on an 11-year cycle. Now here's the point Jeff would really quibble with. I'm not an expert on this, so I can't say. This is just the data I've been presented with. But they say if you fit the best fit straight line here, then you get this line through all this data, and it's a downward trend. So according to this, the sun is slightly cooling off over the last 70 years. Now there is a school of thought out there. We'll mention the oil companies shortly, but there are some scientists, very few, but there are some that write papers saying it's not human caused, it's natural variability, or it's the sun is heating up, or it's something else, we're not sure, but it certainly isn't human caused. Well, if you believe this data, this says no. This says the sun's temperature over this period of interest has been declining slightly by 0.1%. And meanwhile, as we saw the temperature, hockey, they call that the hockey stick, goes along, and then whoosh. We don't see that here. Plus, remember in that data, you saw it bouncing around. You didn't see any sign of an 11-year cycle. So if the sun was really driving it, we should see some imprint on that data. You should see that, but you don't. That suggests that the sun is not a factor. Okay, so we're ruling out the sun tentatively. Now, this is another point that was made by the denialist school. They said, well, sure, the temperature was kind of steady here, 50s, 60s, 70s, and then it started going up around 70. Yeah, it started climbing. But then look, if we ignore this, the last 10 years, then look, 98 it was here, 2006 it was there. It was slightly down over a 10-year period. Global warming has stopped. Whatever was causing it to warm up originally has now stopped. It's just a temporary fluctuation. But then we have all lived the last 10 years. So, well, okay, that doesn't work anymore. Okay, now here's the projections. 1900 until 2100. Well, we're now right here. We're 2020, so we're about right here. Yeah, here's our little spike, our recent spike, the last few years. Now you see again the same thing again. It bobbles around. It was slightly increasing, just slowly, but then 1970, whoop, starts going up fast, and now it's going up really fast. Now, what's it going to do in the next 50 years? Here's 3 projections. This is assuming we stop burning all oil, natural gas, coal. We stop tomorrow morning. Do you think that's going to happen? Let's ignore that one. This is if we put no controls on anything. We just proceed with business as usual. This is capitalism. Let's make money. Profit is the only thing that matters. That's this. That puts you up 8 degrees by the end of the century. 8 degrees Celsius. That's 18 degrees Fahrenheit. That's game over for civilization. We can't grow crops. I'm not saying the last human being would die, but civilization would end. There might be some small society eking out an existence in Antarctica, but this is utter catastrophe. Let's hope we're somewhere down here in this range. If this is the middle range of their projections, that gives us a 4. Oh, sorry. This is Fahrenheit, not Celsius. So that should be 8 degrees Fahrenheit increase. Same thing applies. An 8-degree rise in the whole planet's temperature is catastrophic. But we're probably somewhere less than that. Assume we come to our senses. Then we'd be 4-degree rise. That's, it hasn't been that hot on this planet in millions of years. Since there's been human beings, it hasn't been that hot. We've never seen a planet, an Earth, that hot. Okay, what are some economic effects that they are projecting? Well, red is economic costs, blue is economic benefits. You see a lot more red than you do blue. What are the benefits? Let's start there. Well, fewer people die up in Michigan from cold in the winter. How many people die in Michigan in the winter? So we save 20 people? I don't know. I mean, those people and their families are important, but what else? We have increased agricultural yields here. This is the Northwest, and this is what they call the Great Plains. Okay, up in the very northern latitude, up in the northern part of the U.S., the grain grows better because higher temperatures makes grain grow faster, if everything else being equal. However, it takes centuries to produce soil that's suitable for grain cropping. You can't just cut down a forest. I mean, they do this in Brazil, you know, in the rainforest, for instance, in the Amazon. They hack down huge swaths of forest. They graze cattle on it for a few years. But the soil it's very thin, it's very depleted. It quickly exhausts the soil. They have to cut down more forest and move on. And they do logging, cattle raising. The soil they cannot start grain farming there. It's not suitable. So you can't move hundreds of miles north where you had your family farm for the last century and just relocate your farm up there. Even if the temperature is right, the soil's not right. So I even question these two, but this is their judgment. I'll say, okay, slightly improved yields up there. They'll allow that. Now, what's bad? Well, increased road damage. That's not the end of the world. Decreased shellfish harvests. Changed water supply and demand in the Southwest. Now, that's serious. You know the drought California is in now. And the wildfires. What do we got here? Wildfires. Where's wildfires? Here. Increased wildfires here. Yeah, well, the Southwest is going to get... So California, that's a sign of things to come. And then we have decreased farming yields in the Southwest, in the Great Plains, and south in the Great Plains in Texas, and in the Midwest. So all across the American grain belt here, decreased yields, corn, wheat, soybeans, going down. Increased energy demand. This is for air conditioning in Phoenix and in Texas. You're going to have a lot more. You're going to require air conditioning. And then you have increased heat-related mortality here, there, Southwest, Great Plains, Southeast, and, yeah, Southeast, even into Florida here. So the trouble is humans are heat generators, and we have to shed the heat to keep moving. We generate heat. Every human being generates about 100 watts. So what do we have, 50 people here maybe? We're generating right in this room 5 kilowatts of heat energy right now, and the air conditioning has to draw that out to keep it comfortable. If we can only shed our heat, humans, you know, we are adapted because we're runners. Did you know we're the best long-distance runners on the planet of any species? It seems remarkable that human beings, we pride ourselves on our brains, and yet there's one physical thing we can do better than any other animal. That's run a long distance. We run because our ancestors ran the prey down, they just ran them to death. We're not very fast, but we can go and go and go for a long time. How can we do that? Because we lost all our fur. We're naked, and so when we sweat, we cool down. And most animals can't do that. Pigs, for instance. Pigs are not very good runners, as you know. So that's our claim to fame, besides our big brains. And when the temperature, the critical variable here is what they call the wet bulb temperature. If you take a thermometer and you wrap a sock around it, a wet sock, and you tie it on a string and swing it around your head, that reading is the wet bulb thermometer temperature. Now, when that temperature hits 35 degrees Celsius, humans die, even in the shade, even if you're not in the sun. It's just because it's that temperature of air, then you can't shed your own body heat. You cook to death. It's a miserable way to die, I've heard.
What temperature is that in Fahrenheit?
35 Celsius is times 2 would be 70, minus a tenth would be 63, plus 32 would be 95. That can't be right. That cannot be right. Yeah, around 100 degrees, people start dying. Yeah. There's been, if you've been reading the news the last year, you've seen in Dubai, in the Mideast, there are some temperatures hit, what, 140 degrees Fahrenheit. You can't last long at 140 degrees, even in the shade. Okay, heat death. Heat-related mortality. Kansas has been some high temps, yeah. Okay, so they say to potential economic effects, every 1 degree rise in the global temperature cuts economic output. The economists have calculated this by something like 1.5%. So each time we go up 1%, you lower the economy. That's the economic effects, but I mean, you can also die. There's physical effects, and here's one thing. This will shock you. I did not know this. The breathing, when you have CO2 at 1,000 parts per million, we're currently at 410, I think. We started before the rise started. It was 280. That's the historical average, and it's been that way for millions and I think tens of millions of years. It hasn't changed above that. So we've gone from, here's 0, here's 280. We're now up half. We're up to about 410, and we're climbing rapidly. It used to climb, the oldest measurements of this sort of thing, are on Mauna Loa on Big Island. They have the Mauna Loa Observatory there, and that's the gold standard for carbon dioxide measurements in our atmosphere. It's clean. We're in the middle of the Pacific, so that the air masses move thousands of miles over clean Pacific Ocean. Excuse me, clean Pacific Ocean. And they've been doing those measurements continuously since the 1950s. So if you look at that graph, which I didn't put up here, but it just ticks up. Every year it goes up 2 parts per million. So it was 280, then 282, 284, and so on. Now, like 2 years ago, it hit 400, and now it started going up in the last 3 years, I think. 3 parts per million. It's starting to accelerate. It's going faster. We're now at 410 and climbing. If the worst case scenario hits, by the end of this century, we could hit 1,000 if this keeps up. Here's what happens if it hits 1,000. Human cognition. You didn't think about carbon dioxide relating to your thinking, did you? But if you raise CO2, they've done lab tests, I guess, on this, some psychologists, and you give people an IQ test or something. If you raise it to 1,000 parts per million, human cognition is cut 21%. You're 21% stupider. Yeah, I don't know. I got a lot of details here, but that one caught my eye. I didn't realize it was going to make us stupid. Okay, here's hurricanes. Now here's, this is present day simulation. These are computer simulations. They put in, they put in all the temperatures they expect, and they say, well, what happens to hurricanes then? Okay, here's the current pattern. This is I don't know what HR stands for, Hurricane Rating 5, I think. It's a Cat 5. Storm category, yeah. So Cat 1 to 5, this is just a tropical storm. That's the lowest. The black is what you're really worried about. That one, the one few weeks ago, hit Miami. It was coming through the Caribbean. It was a 5, and then it dropped to a 4. I think by the time it hit Florida, it was down to a 3 or a 2 even. And they were worried it was going to go right up the center of Florida. It kind of veered off. It barely got the west coast, so we dodged a bullet there. But so this is now. And you see where most hurricanes are in the Pacific. Well, here's the Atlantic. No, I shouldn't say that. They hit the East Coast regularly. They come into the Gulf here. There's, Houston in there is where we had the Harvey So, but most of them are in the North Pacific, and then there's a bunch in the South Pacific, and then over here in the Indian Ocean even. So this is now. This is late 21st century. This is 50 years from now. Now, Maui, this is what you're gonna, this is your take home. Maui is 204 east longitude, here's 180 and 210, so that's 30, that's 195 there. So 204 is right here, and it's 21 degrees north. There's the equator, and 20, let's see, you get 15. So 20 is right. Is that Maui there? Yeah. Oops, 204. I'm too high, sorry. 0, 15. Oh, here we go. Here's Maui. Okay, there's Big Island, there's Maui right there. So you see, we're pretty clean. We get occasional tropical storm a little bit to the north of us typically, but we're in the free pass zone. Now look at it at the end of the century here. We're zero right here, 0, 204. You can't even see Maui anymore. It's buried by hurricanes. Hurricanes, yeah. And these are red and yellow, red, orange. We're looking at Cat 4 hurricanes hitting the islands regularly.
What year is this?
This is 50. We don't have to worry about it. Unless things speed up. Okay, now this is the key statement out of this 600-page report. Read this. I'm going to read this out loud. Unanticipated and difficult or impossible to manage changes in the climate system are possible throughout the next century as critical thresholds are crossed and multiple climate-related extreme events occur simultaneously. Now, what do they mean by that last thing? Multiple climate change. Unanticipated. Unanticipated is, let's say, in the Arctic. There's a lot of methane. The Arctic, used to have dinosaurs, palm trees at one time. So there's a lot of dead life buried in it. There's oil. The Exxon wants to go in and start drilling the oil. I'm drilling the Arctic for more oil. But there's a lot of carbon buried in the Arctic, under the seabed. As that seabed warms up, that methane becomes the seabed. The freezing stops. The permafrost in Alaska and the undersea in the Arctic, if they heat up, they will release that methane. Now, about 10 years ago, Russian scientists up there on research vessels started seeing these big plumes of methane coming up in the ocean, about 100 meters across, bubbling up, just churning up methane. So it's coming out. In the last couple of years, those 100-meter vents have opened up to 1 kilometer. There are now 1-kilometer stretches of ocean where methane is bubbling up. So, methane is far more potent as a greenhouse gas than carbon dioxide. It depends on how long a time frame you're talking about. In the short term, it's really potent. Short term being a few decades, 20, 30 years. It's 80 times more potent than CO2. In the long term, being closer to a century, it's still about 40 times as potent as CO2. So the risk, what that unanticipated means is that if this methane comes up, it's adding greenhouse gas to the atmosphere. That's a positive feedback. It's going to speed up warming. Now, how much is it speeding up? Is it a tiny blip on top of the CO2? Or at some point, does it become equal to the CO2 or more than the CO2? Then you would have a positive feedback loop going. It would just be a runaway train. It would just get hotter and hotter. The hotter it got, the more methane would come up. It would speed up. So it would be an exponential rise in temperature. We'd go to that 8 degrees increase. That'd be the end. Sounds pretty dramatic when you say it like that, doesn't it? Okay, I've tried to be neutral here. Now that's the end of the talk. Thank you very much. But I left time. I think we got time, JD. We still got time for questions, right? I tried to keep it short.
People want to leave, we'll let them leave without...
Yeah, anybody that wants to stick around and discuss a little bit, I'll take questions. And online folks, send in your questions however you can. Yes.
Okay, so when you say,
Through what?
Through YouTube, the live feed YouTube.
Okay, that's the PS1 Puka email, PS1 Puka URL.
Just the YouTube live feed.
Oh, okay, if you're on the, folks online, if you're on the YouTube live feed, you should be able to directly submit questions, and we'll read them here. Okay, question here.
when you say the end,
Yes.
let's just say that all this happens and humans become extinct and life, just there's no life.
Yeah.
Is there a point where the Earth kind of corrects itself? Because if you're looking at millions and millions of years,
Yeah.
is there a point where all this happens and then
Sure.
it goes back to ice again?
Sure. The Earth doesn't care about us. The Earth's been through worse. What's that? Oh, yes, repeat the question. The question is, if worst case scenario happens, and first of all, well, here's the question. Then, will the Earth self-correct eventually and forget about this nightmare and return to a nice, happy planet? Yes. The Earth has seen worse than us. We're a temporary condition. And I don't think humans are going to go extinct, because humans are pretty clever, and there will be some place on the planet that's still nice to live, like Antarctica. But civilization may well be in danger, because once the grain stops, you can't feed 8 billion people anymore. So you couldn't support our current population. Now, could 1 billion people survive? Could 100 million people survive in Antarctica, or 10 million, or 1 million or something? Could we have one city in Antarctica left? Sure. Who knows? I don't know. Suppose it's possible. I find it unlikely. Even if we had the worst case, there was 8-degree rise, there's still some place on the planet that's okay. It's just, it's not the main continents that we live on now. So it's going to be expensive to move to Antarctica and start over, rebuild cities. Then it starts you thinking down this train of thought. I mean, this would make a great science fiction story, you know. Humanity clings to survival in the South Pole, and they start civilization up painfully and slowly again. Do they do the same thing all over again?
Yeah.
Surely not.
But my question was the planet, the Earth.
The planet, yes.
Millions of years.
Yeah, the question, let's try to get back to the question, which is the planet. The planet will slowly reabsorb. I mean, once we stop civilization, if civilization stops, then we're going to stop burning oil, of course. And so we stop polluting the atmosphere with CO2, and it will gradually be weathered out, but it takes thousands of years, maybe tens of thousands of years before it would recover. But 50,000 years from now, we're long gone. The Earth will recover. Now, the problem is life may not recover. We are currently in the 6th mass extinction, and it's caused by us. There's been 5 previously. Now, you've heard about the dinosaurs. They got hit 64 million years ago, I think, and wiped them out. That was an asteroid. But the other 4 mass extinctions were not asteroids. They were rises in CO2, either caused by volcanoes or I haven't looked into every one in detail, but all 4 were caused by a sharp rise in CO2, much slower than what we're currently doing. They were over thousands of years, not in decades like we're doing. So we're now raising the temperature at the fastest rate ever recorded that they can reconstruct. At least 10 times faster. There's never been anything like this on this planet, this fast of a rise in temperature, or this fast of a rise in CO2 in a matter of a few decades, where we've increased the CO2 level by half. That's huge. You're talking parts per million. You think, well, it couldn't possibly matter that much. It does. It's a greenhouse gas. You can do it in a laboratory. You can make a box with CO2, a box with oxygen. This one, you shine a light in. This one heats up. This one doesn't. The physics is plain and simple. There's no question about it. So yes, the answer is the Earth will recover. But in the let's see, number 5 extinction was the dinosaurs. It was 64 million years ago. Number 4 was 250 million years ago. I'm not sure that's number 4 or number 3. Anyway, the one that was 252 million years ago was due to a sharp rise in carbon dioxide. Temperature skyrocketed. 97% of the species on Earth died, both on the land and in the ocean. 97%. So, if that happened, say, in the next century or two, then the life would not recover quickly. Evolution is slow. The average species survives about 3 million years on average. We've only been around, what, 200,000–300,000 years. Modern Homo sapiens sapiens, us. So 250,000 years for us. We're young as a species goes. It's not clear we're going to get our full 3-year allotment. Yep, question in the back.
Can you say anything about the possible weight redistribution with the poles, ice caps melting?
Good question.
And could that shift the poles or
Very good question. If the ice melts, the ice is melting. If it continues to melt and it all goes away, then the question is, will that shift the mass distribution of the planet and change its rotation or orbit or something? Now, first of all, that brings up a good point about what the cause of the 100,000-year ice age cycle is, and that's orbital. So the Earth tips. It goes through, it's precessing. It's like a spinning top. But you know how a top is spinning fast, but it also precesses, right? It goes slowly around like this. So the Earth does that too. It spins fast once a day, but over thousands of years, it slowly spins around. So the North Star is not fixed. It slowly I think it's a 27,000-year cycle. So over time, our North Pole slowly rotates around. That's what's causing these 100,000-year cycles. The Earth's orbit changes. Its tilt changes slightly every 100,000 years. It goes back and forth. When it points, here's the sun. When the Earth points closer to the sun, the poles then, in the summertime, the North Pole, and in the South Hemisphere's summertime, in the South Pole, they point closer to the sun. They get more heat. That heats up the whole planet more. When the Earth straightens up again more, then the heat goes into the equator, the poles stay colder, then you have a cooler overall average. So that explains that 8-degree shift. When the Earth tips in closer, it gets hotter. You have the interglacial, the period when it jumps up, and then it slowly gets back to the opposite configuration, and then the temperature drops for 100,000 years, ice age, and then interglacial. So that's why that's so regular. Now the question was, will that change surprisingly, the ice in the Arctic and Greenland and Antarctica is a sizable amount of mass. It actually does have an effect on the Earth. And when that melts, it will have some effect on the orbit, and I don't know if anybody has tried to calculate what the effect would be. I don't know, sorry. It'll have some effect on the spin of the Earth, yeah, like just melting Greenland, I think, because the other two are on the poles. So if it's spinning on the poles, you think, well, that's not a big factor. But if you're off the poles out here and you're swinging this mass around and it goes away, then you can see that throws things off. It's like a top with a little lead weight on the side or something. You take that on and off, it changes its spin. But, sorry, I don't know if the answer is known to that. Yep.
It's an 11,000-year interglacial cycle, but we probably still have another 1,000 years to go.
No, it's not that precise. It varies from 5 to 15. It's something around 10 plus or minus 5, so it changes depending on.
We can't count on another ice age to cool us off.
No, no, no. That could be thousands of years away. We've had 10,000 years of good weather and great crops. You would normally have expected that would end within 5,000 years, more say. It was sometime in there it would stop, and we'd go into an ice age. Now, if we heat up, or we are heating up, if we continue to heat up, then we will negate the next ice age. We won't go into that ice age, and they do say that clearly. So we've changed. You know, that's a big change in the Earth's history. We've now interrupted things. So when would we go in? Well, at the moment, we're not going into the next ice age unless we quickly return conditions to normal. Well, then you get close. 1,000 years from now, we realize, hey, another 1,000 years, we're going to hit the ice age. Then we might want to do something to intervene. We might want to pump CO2 into the atmosphere or something like that, you know. But that's far in the future. What we're worried about is right now and staying alive. So that's the immediate problem for animals, is today, not 1,000 years from now. You know? So now there's another point there that connects to when you read these articles in the newspaper, they keep talking about 2 degrees, 2 degrees. We can't go over 2 degrees. That's 2 degrees Celsius, by the way. What's so important about 2 degrees? Why not 3 degrees? Why not 1 degree? Okay, when you saw that the ice age is here, and then we jump up into the interglacial, the noise up here, while you're in the interglacial, that 10,000 years or so, that's about 2 degrees thick. So once you bust out of 2 degrees, you're into uncharted territory. Now we're going into something that hasn't existed in millions of years on this planet. We don't know what's going to happen then. So, like Walter Brocker said, Brocker, a famous climate scientist, he said the atmosphere is an angry beast, and we're poking it with a stick. Any questions online, or?
First of all, Stefan over at Coronado Shores says hi.
Hi, Stefan, and everybody at Coronado Shores. How y'all doing? That's our former. Well, he's still our IT person. She's our IT person here, and she's now semi-retired, but she still helps keep the computers running around here, and she has a crowd watching online. Less than a second different, the rotation rate, if the poles melted. Okay, so there you go. That's an answer. Who said that, Stefan?
No,
You Googled it. JD's on the spot. Okay, so second gets a a second longer. We change our clocks, you know, big deal. Yep. We'll be skinnier, too. We'll be hungry. No. The question is, besides being stupider, will breathing be a problem? No, it's off the top here. The breathing is a problem. Not for me, because I'm male, but pregnant women... pregnant ozone likely is 70% higher by mid-century. That's in 30 years. Pregnant women exposed to that increases autism tenfold. I've got a whole list of things like that if you want to read this sheet. These are projections, so I'm not a prophet. I can't tell you what for sure, but these are the best minds in the American government scientific community, and this is what they expect. So I'm just the messenger here. Yep.
So in the short term, I think it was 2050, you mentioned shellfish. What about other fish in the ocean?
Oh, question is, shellfish were indicated to be in trouble. What about fish in the ocean? The fish in the ocean are already in trouble, regardless of, because of acidification, which I haven't even mentioned. The CO2 that we're pumping out and that they were wondering, there was a discrepancy. The model said it should be going even faster, but it turns out that most of the heat, 4/5 of the heat, extra heat that is a consequence of the greenhouse gas, has not been going into the atmosphere, it's been going into the ocean. So the ocean is heating up much faster than the atmosphere. Now that won't go on indefinitely. Eventually the ocean will have had its fill with heat, and it'll start dumping that heat into the atmosphere. So we've bought some time. This is very fortunate. 80% of the heat has gone into the ocean so far. The deep ocean, not the surface ocean even. When we measure, when I talk about these global temperatures, I'm talking about a global average of land and water, like the British Navy and their buckets of water, you know. That deep ocean is going to give up its heat eventually, and then things are going to accelerate. Now, sorry, what was the question? Fish. We've already wiped out most, I mean, the tuna, ahi is already down 90% in the Pacific, isn't that right, in the Pacific Ocean? We've just fished out the oceans. That's a fait accompli. We're now, the fish that we eat in the market, the premium cuts of fish don't exist anymore. We're now eating fish that used to be considered throwaway bottom fish. They weren't worth it. So we probably aren't aware of it because it happens slowly, but our diet has already been degraded, or taste at least. I don't know if it's food quality is probably okay, but the fish that people used to love, they're gone already. But yes, it'll cause huge damage to corals. For instance, the Great Barrier Reef, which is one of the wonders of the world. Last year, it took a huge hit, lost 30, I think the 30%, something on that order, of the Great Barrier Reef was bleached white. Now, they can recover from that. If it's temporary, then sometimes the corals will come back. They expel algae, there you go. And then, okay, you can recover from that, but if it happens 2 or 3 times in a row, then it's just dead. So we're waiting to see what happens next summer. And at the same time that the Australian tourist industry is getting hammered by this, bad publicity and so on, it hasn't hit the actual favorite tourist spots yet, so it hasn't hit them hugely economically, but you can see what's coming. At the same time, Australia is about to build the biggest coal plant ever and so on. So, the coral is impacted not only by the heat, by the temperature, but by the acidity. The CO2 absorbed into the ocean makes carbonic acid, and then that dissolves the shells of a lot of sea organisms, so they can't reproduce anymore. They'll just disappear. Yeah, next, yeah. So say again. So, somebody says what? Oh, okay, I knew this was going to come. You're going to put me on the spot. The question is, do I believe in climate change? Duh. Well, you've seen the temperature. I mean, okay, I'll take a stand here. Yes, it's clear, and it's not a belief system. I'm trying to stick this to evidence. We're not talking philosophy here. So the evidence, I think, clearly indicates, unmistakably indicates that we have warmed up 1.1 or 1.2 degrees Celsius, over 2 degrees Fahrenheit already. And you can see the plot. And if you believe the reasoning of the CO2 and you look at the oil being burned, and then it indicates we're headed for trouble. Now, how bad is that trouble? Is it something we can deal with? Just put a tax on carbon and keep going business as usual and get along? Maybe we got to run our air conditioners more or whatever. Or is it the original title I had for this talk was Bye-Bye Cornflakes. If you wipe out the Midwest grain belt, then America is not the grain producer for the planet anymore. And so once the grain is gone, civilization is gone. That's what it looks like. And I think, okay, what are the odds? Well, you got best case, middle case, worst case. best case, I don't think it's going to happen. We're not going to stop burning oil right away. That's why I think it's important for scientists to talk about this now. Unless people realize, really sinks in what's happening, and we take action immediately, then it's going to be too late. 10, 20 years from now, it's too late. It has to happen. We have to start doing something. I mean, because this thing takes time. You can't just shut down our whole economy is based on oil. You can't just shut that down overnight. It takes, we have to replace it with renewables, solar, wind, whatever. There is encouraging signs. The cost of solar is coming down rapidly, and they say within 10 years it'll be competitive. You know, already people, I have solar panels, a lot of people, you probably do too, on your houses, just because people want to do the right thing. You know, you don't want to be contributing to the destruction. But 10 years from now, you saw we were going up 1/10 of a degree per year the last 3 years. If that continued for 10 years, that's a 1 degree in 1 decade. That puts us 2 degrees Celsius. That's almost 4 degrees Fahrenheit right there. So worst case, we could hit that in 2030, which when most of us will still be alive. Certainly our children are going to face radically different conditions, and our grandchildren are going to be living on a different planet. If we don't act immediately, if the people have the power. Okay, now I'm going to really get myself in trouble. Why is this happening? It's because we have a class-divided society. We have capitalism. Now, capitalism has delivered a lot of benefits, wealth, great wealth to this planet. But the people that make the decisions are making them based on their wealth and power. They want to maintain the status quo. They want to continue their wealth and power, those families at the top that own everything. The rest of us, we want to do the right thing. We want human welfare. We want to stay alive. They think, I'm speculating, just so you know, but I think they think that they'll be exempt because they're so used that, you know, America's been here. We've had a ruling class for 500 years. It's the longest existing ruling class in history. These families don't think they're going to get hurt. They think, I don't care what happens. I'm going to drill the Arctic. I'm going to pump the oil. 4/5 of the oil is still underground. What we've burned so far in the last 200 years, last 150 years, is only 1/5 of the oil. If we burn the other 4/5, it's game over. So we have to leave the oil in the ground. Sooner is better than later, like sooner being like right now. Later is 20 years from now. It's not very far off. So these families, I think, they can't conceive that they will, I don't know. I'm not a psychologist. You figure it out, but it's not happening. Yeah.
So Mark, would you mind adding in my comment?
Yes.
The rich that do adapt.
Yeah. Okay, that's JD's point. We've had this discussion, and he's saying, well, Mark, you're bad-mouthing capitalism, but capitalism has brought us technological wonders. We have iPhones, we have television, we have airliners. And so it's in the interest of some clever capitalist to figure out how to make money on this. Well, the Chinese are doing exactly that. They're lowering the cost of solar cells. America's way behind. And that's the bright spot on the horizon. The problem is it's not happening fast enough, and we're running out of time. 30 years ago, 85% of the energy was produced, worldwide was produced by fossil fuel, coal, oil. Now it's dropped to 81%. That's in 30 years. It's not happening very fast. Unless we take really drastic action very soon, like now, we're not going to get there in time. Solar cells are not going to save us. It's just not happening. We wait 10 more years. I don't know. Maybe we can wait 10 years and get away with it. But there's those unanticipated and difficult or impossible to manage changes. The methane cuts loose. If that happens in 10 years, then it doesn't matter what you do after that. It's a runaway train. So we're, like you said, we're poking the angry beast with a stick. we don't know what's going to happen. We should back off and think about this just for caution. Yeah. Yep.
Let's have some discussion afterwards so that anyone who wants to.
Okay, thank you very much, folks. Stick around and talk if you want. I'll be here.